Hello everyone. This lecture of dynamics of the lithosphere is about viscous creep, and this is part number 1. You already see a beautiful picture of the Morkel fold nap on the title slide. Let's zoom a little bit on it. So you see this cliff here. It shows you a fold, so you have rocks of different colors, from brownish, yellowish, reddish, black and grayish, and this shows you a beautiful shape of a fold. So this is just to illustrate that rocks do record permanent deformation and they can accommodate large strain. So that is an important mode of deformation within the lithosphere. If you want to see this place, it's in Morkel in the Swiss Alps. It's a fantastic outcrop. So elastic deformation is what we discussed until now, and they do matter for lithospheric flexure, for example. That's what we discussed over the last lectures. But beyond elasticity, we also need to explain the occurrence of permanent deformation, which are ubiquitous in the lithosphere. So for example, in the crust, you will know that there is faulting. In the lower crust, there can be creep, channel flow, folding, necking, or diapirism. The lithosphere, in the region of subduction, for example, the plates are bending, and part of this bending is, of course, irreversible deformation, so permanent. And the lithosphere below is undergoing convection, so materials needs to creep. This is what we were referring to as a fluid mantle in the previous lecture. So just to briefly rediscuss elasticity and highlight the differences between elasticity and viscosity and plasticity. Here I will just state that the elastic deformations are reversible deformations. So if the guy here step out of the board will go back to a flat configuration. So in the rocks, it mostly occurs for very small strains. And the strain energy is stored and can be recovered during elastic deformation, such that there is no entropy production associated to elastic deformation. An example of elastic deformation is the motion of the wave, elastic wave in rocks. So the travel of a seismic wave does not alter the material permanently. So when the wave is traveling through the rock, once the wave has passed through, the medium is left undeformed. So the deformation is reversible. The same would apply for the flexure of the lithosphere. Last week we were studying the loading of a plate, but in the case of elastic flexure, if we would remove the load on top of the plate, then the plate would recover its original shape. So that's a big difference now when we talk about inelastic deformations. Inelastic deformation are those which are irreversible, and that's basically viscous deformation and plastic deformation. With inelastic deformation, large strains can be experienced by the rocks, and they may be exhibited in shear zones, faults, the occurrence of folds and necks in rocks. So the strain energy is dissipated partly as heat, and there is entropy production during viscous deformation and plastic deformation. Yes, if you would remove the applied force, a mountain belt would not unfold after orogeny. So the deformations are indeed permanent. Another example here at the smaller scale, this is a shear zone in taken in Neves Glacier, Südtirol. You see that shear zones are recording the localization of deformation inside the rocks, and the same, these are permanent deformation. So another example of permanent deformation is the occurrence of faults. So you see a beautiful example of a fault on this picture here. We have a normal fault here, and this deformation is also permanent. At the scale of the lithosphere, inelastic or permanent deformation matter a lot because they're responsible for they control the overall architecture of the lithosphere. So that's here a very nice cross section through the Alps, where you can see a multitude of structures which are related to inelastic deformation. So first you have the subduction or the underthrusting of the European crust below the Adriatic plate here, and you see a multitude of faults which are affecting the outer part here of the Adriatic plate, and you see also a lot of faulting and overthrusting here in this unit in the Jura, and ductile nap formation and backfolding in the internal sections of the Alps. All of these structures are permanent deformation structures, so they do matter a lot for the lithosphere. So remember elasticity. With elasticity, stress was increasing as a function of the strain. So we had this type of diagram with stress and strain on one axis, and the slope of the lines was corresponding to some elastic modulus, for example, the Young's modulus. So here's the relationship: sigma equal E times epsilon, where sigma as unit Pascal, epsilon is strain as no unit, and the Young modulus E as unit Pascal. So let's make Pascal is equal to Pascal. The elasticity affects both shear and volumetric deformation. For example, we have the occurrence of P waves, which are associated to volumetric deformation, and S waves, which are mostly deviatoric. There is no dependence on time, so we talk about time independent behavior. The rate at which the deformation occurs has no effect. So if you're doing a bit of stretching, it doesn't matter if you move the leg slow or fast. What matters is how much you will stretch. It's not how fast you stretch. So here, strain is what matters, what controls the magnitude of stress. In viscosity, in viscous materials, we relate the deviatoric stress as function of the strain rate, not as function of the strain. So now we have a different type of diagram. Here we have the stress, or the deviatoric stress. We'll come back to this term deviatoric a bit later in the lecture. So the stress, and now it's plotted against the strain rate. So on this diagram, we have stress is equal a modulus here, eta, times epsilon dot. So epsilon dot is the rate of the strain. So what are the units involved here? We have Pascal here. We have strain, which has no unit, but you take the rate of something which has no unit. This is 1/seconds. And so we have a modulus here that multiplies something in unit 1/seconds in order to obtain something in unit Pascal. This factor eta should have unit Pascal times seconds. So viscosity, it only affects a shear or deviatoric deformation, and it's usually incompressible. So there is a dependence now on time. The rate at which the deformation occurs matters. So an example of a viscous deformation is, for example, the cheese fondue. It's viscous, and if you stir it very fast, it will become more difficult to stir. Chocolate fondue is also a good example. It's really viscous, and you see here, you can imagine this as a slightly lower viscosity than the cheese fondue. But it's not only about food. Viscous deformation, they also matter for rocks, and that's an example of a tombstone here, which has been deforming. So you see a slab of rock which is bent downwards, and this is not an elastic deformation, it is a plastic viscous deformation that required time to occur. So this rock is under the gravity loading, and with time it's been creeping and develop a sag shape here, which is a permanent deformation. So rocks do creep, and the creep takes time, so rocks are viscous. Pitch is known as a high viscosity fluid, and actually an experiment was started in 1927 in Queensland University, and they put some pitch into a little bucket here with a hole, and the pitch is flowing down. It's viscous, it's flowing down under gravity, and it's making 1 drop approximately per decade. So it's the Guinness World Record of the longest experiment since 1927. So you see recording from 38 here to 2014, and you basically see only a few drops. So it looks like a solid, but it actually flows on the long term. So the long term here is several decades. To give you an idea of the order of magnitude, the viscosity of pitch is 2.3 10 to the power 8 Pascal times seconds. This is a very high viscosity fluid already, but this is nothing compared to estimated rock viscosities. We'll come back to that later. Now we need to discuss compressibility and incompressibility. So what is compressibility? It's basically the capacity of a material to change its density upon a deformation. So if deformation are linked to volume changes, they are volumetric deformation. Think about this material here. This could be, for example, a gas in a box with a load on top. If you change the weight of the load, you make it really large, then you see that the volume is decreasing. So the material here is compacting under a deformation. This also implies that the density of the material here is increasing with compaction. So that's the case of a compressible fluid. So this can be a gas, for example. In elasticity, so rocks are compressible elastically. We had a measure which was the Poisson ratio, which was measuring the actual the ratio of actual deformations, and we even had measure, so the Poisson ratio is ranging from 0.2 to 0.5, and you derive this as an exercise. 0.5 was corresponding to the incompressible limit. So what's now incompressibility? Incompressibility is this situation. So you already have a material here, in the box and you change the weight on top of it, and the surface here, or the volume, will not change. So this material is incompressible. The material does not compact and does not dilate. The density also does not change under this load here. And this is the case of viscous deformation in general. We say that these deformations are virtually incompressible. So another way to discuss compressibility is to consider an infinitesimal volume of fluid. So we have a fluid volume of delta x and delta y. The top side has a size delta x, as the bottom does have a size delta x, and same for the sides, they have the same size. Here we have an inlet velocity vx, and we have an outlet velocity v at position x plus delta x. If we compute the velocity gradient along x, so it's dv dx, is the limit as delta x reaches 0 of the difference vx plus delta x minus vx divided by delta x. That's dvx dx. Now, let's consider that the outlet velocity vx plus delta x is large and positive. So material is flowing more than it is inflowing. So if v at x plus delta x is larger than vx, then dv dx will be larger than 0. The material should then expand, and the density should decrease. This is a dilation case. The opposite can be obtained if the inlet velocity is larger than the outlet velocity, the inflow is larger. You have vx plus delta x is smaller than vx, dv dx is smaller than 0. The material in this case should compact and the density should increase. So if the two velocities are equal, then dvx dx is equal to 0, no compaction and no density changes. So that's for the incompressible case in one dimension. But in 2D and 3D, there is more freedom. So if you consider inflow and outflow in the vertical direction, you have more possibilities to vary the different values on the sides of this infinitesimal volume. What matters here is that for incompressible flow, the condition of incompressibility should be respected, so such that dvx dx plus dvy dy plus dvz dz should sum up to 0. There is no net change of mass. And to deal with incompressible flows, we need to include or to introduce now the notion of total and deviatoric strains and stresses. So the term deviatoric was used in the previous slides, and now we should define what I'm referring to. In elasticity, we've been always relating stress sigma to strain epsilon. These are total deformation. These are total stresses and total deformations. That's what we've used so far. But a deformation of a material can take can happen in different fashion. One can be the volumetric deformation, which is a change of volume. So if you change this big square into a small square, this is shrinking. We have a volumetric deformation. To measure the volumetric deformation, we've computed the divergence of the displacement, for example, epsilon kk, and there's a pressure associated with this, a pressure change associated with this deformation. Another type of deformation is a deviatoric part. So the deviatoric deformation is a change of the shape, but with no change of the volume. And these are associated to deviatoric stresses and deviatoric strains, epsilon prime. So for example, a pure shear deformation, you would squeeze this square and you obtain a rectangle of the same volume. This is a change of shape with no change of volume. The viscous deformation, they are mostly incompressible. So we will try to only consider the change of shapes associated to this deformation. So we will only deal with deviatoric parts. So how to filter out the volumetric part of a tensor field? We need to remove the mean of the diagonal elements from the diagonal elements. What does it mean? Consider a 2D total stress tensor. So sigma ij, that's sigma xx, xy, yx, and yy. What we're going to do, we're going to compute the deviator, and the deviator is the original tensor, or the total stress, minus the trace, which is the sum of the diagonal elements, this thing here, sigma xx plus sigma yy, divided by the number of dimensions. So here it's 2D, divided by 2, this makes a mean, times delta ij. This means that this subtraction is only applied to the diagonal elements. This is how to compute a deviatoric tensor from a total tensor. Sum the diagonal, divide by the number of dimensions, and remove it from the diagonal of the total stress tensor here. So that's how to write the deviatoric stress tensor now as a function of the total stress tensor and the pressure. So the pressure is the negative of the mean of the diagonal of the total stress tensor. So you can simply write the deviatoric stress as sigma xx plus p, so p being minus 1 over 2 sigma xx plus sigma yy for a two-dimensional case. The same p can be added to this second diagonal term to produce the deviatoric stress tensor. Once again, delta ij implies that this subtraction or addition of a pressure is only applied to the diagonal terms, so nothing will affect the off-diagonal terms. So in the deviatoric tensor, the off-diagonal terms will be original to the total ones. So one can write up the deviatoric stress as a function of a total stress and a pressure. So there's a fundamental result here, is that the trace of the deviatoric tensors are 0. So you can easily check this. It's valid for all deviatoric tensors, stress, strain, strain rate tensor. In the case of viscous deformation, they are virtually incompressible, so we are going to cross out this entire part here, and the viscous constitutive law, they are going to be written in relation to strain rate. So the stress, the deviatoric stress, will be related to the strain rate, and here we have the viscosity and the factor 2. The volumetric part, you see, is not addressed here. There is no constitutive law for obtaining the pressure, for example, here. So the pressure is not defined by the rheology. So let's go back to expliciting the deviatoric strain rate and the deviatoric stress tensor. So in most cases, these tensors are actually symmetric. So this means that epsilon dot prime xy is equal epsilon dot prime yx. So if you write up the table, so you have the strain rate and you take the deviatoric part of this strain rate, all the normal terms, epsilon xx, yy, and yz, and zz, their sum should be 0 because it's a deviatoric tensor, and the terms are symmetric. The same applies for the deviatoric stress. Tau xx plus tau yy plus tau zz will be equal to 0, and tau xy is equal to tau yx, and so on. They can be reduced again to vector notation. So in 3D, we end up with 6-component vector for the deviatoric strain rate, and for the deviatoric stress too. And finally, we can write up the constitutive relationship for an isotropic fluid. So this applies for isotropic material. It's worth being stated. So we have the stress component on the left-hand side, 6 components, and the deviatoric strain rate on that side. And now you see the relationship is very trivial, as the coefficient matrix here only features 2 eta on the diagonal. There is no off-diagonal term as we had for the case of elasticity using a total stress formulation. So there's one single parameter, and that's the dynamic viscosity, which we will be using a lot in the exercises. So the dynamic viscosity, eta is unit Pascal times second again. That's the slope on the deviatoric stress versus deviatoric strain rate diagram. So that's to summarize this first part on viscous deformation. So the viscous deformations, they are essential to explain the observed continuous deformation of rocks within the whole lithosphere. They are different from elastic deformation. They produce irreversible deformation, and they're mostly incompressible. And in the case of viscous deformation, the deviatoric stress is related to the deviatoric strain rate via the viscosity. So that's it for the first part of the lecture. Thanks for your attention.